Buckle up, everybody, because today we are taking a deep dive into something that's like seriously mind-blowing.
Yeah.
We're talking about Einstein's famous equation E equals mc².
You got it.
And get this, our listeners are always asking the most amazing questions, right?
Absolutely.
So one of them actually reached out and was like, wait a minute, is E equals mc² like the whole story? Or is there something more to it?
Yeah.
And with the source material we dug into for this deep dive, it kind of suggests that there might be
It really does.
some cracks in that iconic equation.
Yeah.
So
yeah.
let's unpack this, for those who might not be, totally fluent in physics lingo.
Sure.
E equals mc² basically means energy equals mass times the speed of light squared.
Exactly.
It's like this super fundamental idea in physics. But the source material we're looking at today throws a bit of a curveball by saying,
it does.
hold on, what if this whole rest mass thing?
Right.
What if it's not really a thing?
What if it's not really a thing?
Now, when we say rest mass, we're talking about the idea that, an object has a certain mass when it's just chilling out and not moving.
Exactly. Like it's at rest.
Yeah, exactly. But our source material is like, what if true rest doesn't even exist? Think about it on a tiny, tiny level.
Yeah.
Atoms, those little particles, they're always buzzing around.
Constantly moving, vibrating, yeah.
Right, and planets, they're spinning.
Rotating.
Solar systems are doing their whole orbit thing around galaxies, and even galaxies are not just sitting still.
Right, galaxies themselves are moving within the universe.
It's like a cosmic dance party out there. Everything's in motion.
It really is a constant state of motion.
So if nothing is ever truly at rest, does E equals mc² even, hold up?
That's the question, isn't it?
Great question.
And the source material suggests that maybe it's not the complete picture. They're proposing this refined universal energy formula.
Ooh, fancy.
I know, right? It sounds very grand. And it's basically like E equals mc² 2.0.
Okay, I'm intrigued. Tell me more.
Well, one of the key things they do is incorporate something called the Lorentz factor.
Okay, I've heard of that, but honestly, I could use a refresher.
Sure. So the Lorentz factor, which is represented by the Greek letter gamma, it basically accounts for the effects of relativity.
Relativity, that's Einstein's whole thing, right?
Yeah, exactly. So as things move faster and faster, their mass actually increases.
Whoa, really?
Yeah, and this effect becomes way more pronounced as you get closer and closer to the speed of light.
So if I was running super, super fast, I would get heavier.
In a sense, yeah, your mass would increase from a relativistic perspective, but it wouldn't be noticeable at everyday speeds.
Oh, 'cause it's not like I need to worry about becoming a black hole if I sprint to catch the bus.
Not quite, no.
Good to know. But so this Lorentz factor,
E
equals mc², doesn't really account for that.
No, it doesn't, but the refined formula does.
So it's like E equals mc² is fine for everyday stuff?
Exactly.
But when things get really speedy.
Yeah, when you're dealing with speeds approaching the speed of light, you need this extra factor to make the math work out.
That makes sense.
But wait, there's more.
Oh, there's more.
There's more.
I love it.
This refined formula also throws in this other component. It looks kind of intimidating. It's like L times A times the Greek letter CII times H with this little hat symbol on it.
Okay, yeah, that sounds like a whole bunch of physics jargon.
It does, but it's basically adding in a bunch of factors that E equals mc² just kind of ignores.
Well, like what?
So first you've got L, which stands for angular momentum that takes care of rotation, like how things are spinning.
So like the Earth spinning on its axis.
Exactly. And then there's A, which represents imbalances or asymmetry in a system.
Imbalances, that's interesting.
Yeah, it's acknowledging that things aren't always perfectly symmetrical.
I see.
Then we've got this Greek letter CI, which comes from quantum mechanics. It represents the wave function.
Oh, quantum mechanics. Now we're getting into some really trippy stuff.
I know, right? And then finally there's H with a little hat on top, which stands for the Hamiltonian.
The Hamiltonian, okay, honestly, that one sounds like something out of a Harry Potter spell.
Right.
So can we break that down a bit? What is the Hamiltonian in normal human speak?
Sure. So basically, the Hamiltonian is a way to represent the total energy of a system. It includes things like the energy of motion, momentum, and position.
Okay.
And also potential energy, like the energy something has stored up because of its position or state.
So it's like a total energy package.
Exactly. It's trying to capture all the different forms of energy that might be present.
That's pretty cool.
Yeah.
So basically, this refined formula is saying, hey, energy is Way more complicated than just mass times the speed of light squared.
Right.
It's about movement, rotation, this whole quantum weirdness.
Yeah, it's a more holistic view of energy.
And all sorts of other things that equals mc² just doesn't really touch on.
It's a more complete and dynamic picture.
So what does this mean, like, practically? Are we saying goodbye to E equals mc²?
No, not necessarily. E equals mc² is still a super useful tool, especially for things that are moving way slower than the speed of light.
So, like, for most everyday situations.
Yeah, exactly. But this refined formula, it could be really crucial for understanding energy in more extreme environments.
Like where?
Like black holes, or the very early universe just after the Big Bang.
Wow.
Places where things are super dense, super hot, and moving at incredible speeds.
That's mind-blowing.
And it might even help us understand energy on the quantum level.
The quantum level always throws me for a loop.
It's pretty wild down there.
But this also shows us that science is like a never-ending journey.
It really is.
Like, we're always learning new things, refining our models, and sometimes even challenging our most cherished ideas.
Exactly. Our understanding is constantly evolving.
That's so exciting, though.
Yeah, it's the beauty of science.
So just to sum this all up, E equals mc² was a huge leap forward. It changed the way we understand the universe, but it might not be the final word on energy.
Right.
This refined formula is making us think beyond rest mass and consider this whole dynamic, interconnected nature of energy.
In a universe where nothing ever truly stands still.
It's like a whole new perspective.
It is, and it leaves us with this really interesting question.
Ooh, I love a good question. Lay it on me.
If energy truly is never at rest,
Yeah.
what does that tell us about the very fabric of reality?
Wow. That's deep.
Something to ponder as you continue exploring the mysteries of the universe.
And on that note, I want to thank everyone for joining us on this incredible deep dive.
It's been a pleasure.
Remember, keep questioning, keep exploring, and until next time, stay curious.
Stay curious.